Hello, AP Chemistry students. We're now on Unit 8, Part 1 on acids and bases. And this covers sections 8.1 through 8.4 and 8.6. So there is a ton to talk about on this one. So this video might be a little long, so you might want to take a break somewhere in between. But luckily, all of the content here is going to be very closely interrelated. So our learning objectives here are to calculate the values of pH and pOH based on Kw and the concentrations of all species present in a neutral solution of water, to calculate pH and pOH based on concentrations of all species in a solution of a strong acid or a strong base, to explain the relationship among pH, pOH, and the concentration of all species in a solution of a monoprotic weak acid or weak base, to explain the relationship among the concentrations of major species in a mixture of weak and strong acids and bases, and then to explain the relationship between the strength of an acid or base and the structure of the molecule or ion. So before we get into it, let's do a little bit of review. We covered briefly what acids and bases are in Unit 4, but that was a while ago, so let's talk about it again. Acids are defined as a chemical species that dissociates into water to produce hydrogen ions, also called protons, since hydrogen only has one electron, and if it's pulled away, all there is a bare proton. And this is the Arrhenius definition of an acid. And then there's also another definition of acid that says an acid is something that donates hydrogen ions or protons to another substance. And this is the Bronsted-Lowry definition. And both of these apply to a lot of acids, especially strong acids, but we'll talk about that in a bit. Some examples of what this looks like. HCl is an acid, and it splits up into hydrogen ions and chloride ions. And this is representing an acid in terms of the Arrhenius definition. And then representing it in terms of a Bronsted-Lowry definition. The same acid, we'd have HCl interacting with a water molecule and donating its hydrogen to the water molecule to make chloride and hydronium, H3O+. And we talked a bit about this in Unit 4, but hydronium and hydrogen ions are basically the same thing. I know they look different, but they are in basically equal equilibrium with each other. Hydronium is just a way to represent hydrogen ions in solution when we want to show the interaction with water, which is going to be important in a lot of cases here. All right, and then bases are defined as a chemical species that either dissociates into water to produce hydroxide ions. This is the Arrhenius definition of a base, or one that accepts hydrogen ions or protons from water or another chemical species. And this is the Bronsted-Lowry definition. So examples of this, I couldn't show two of the same base interacting because the Arrhenius definition basically only applies to strong bases, and the Bronsted-Lowry definition only applies to weak bases. But like I said, we'll talk a little bit more about that distinction later. So in the Arrhenius definition, we have KOH splitting up to make K or K plus potassium ions in solution and hydroxide ions. And then for a Bronsted-Lowry type base equation, here we have ammonia that is going to be interacting with water. And instead of giving a hydrogen to water like it did in the acid case, it's going to take a hydrogen from water and become ammonium, NH4+, and then that produces hydroxide in solution. So in both cases, you're going to end up with hydroxide, but sometimes it's either going to be a direct release of hydroxide in solution through dissociation. This is strong bases or Arrhenius bases. And then here it's more of an indirect one. The hydroxide is being formed from water molecules as the base removes a hydrogen from them. So some acids and bases can be strong, meaning they dissociate or split up completely. So if you have HNO3, nitric acid, this is a strong acid. It's basically going to entirely split up into hydrogen ions and nitrate ions. Same thing for strong bases. They're going to split up into their metal cation and hydroxide. Now, some acids and bases are weak. And what that means is that the amount by which they dissociate will be based on their equilibrium constant, either Ka or Kb. So hydrofluoric acid, HF, this is a weak acid, and it will split up into hydrogen ions and fluoride ions. But the Ka for this process is 6.6 times 10 to the negative 4. So this small equilibrium constant tells us this is more of a reactant favored process. So most of the HFs are not going to split up. We are going to get some hydrogen ions in solution, meaning this does behave as an acid. There will be hydrogen ions in the solution to make it acidic, but it's not happening to the same extent as something that a strong acid would. And strong bases, weak bases are similar. And like I said before, the weak bases mainly apply to the Bronsted-Lowry definition of accepting hydrogen ions from other substances. So here we have, I think it's called pyridine, C5H5N. This is a weak base. It's going to remove hydrogen from water to make C5H5NH plus, and then hydroxide ions in solution. And much like the HF example, we see that the equilibrium constant here is pretty small. So this means it's mainly reactive favorite, and this is only happening to a small extent. So in summation, for a strong acid or a strong base, our Ka or our Kb value is going to be way bigger than 1, to the point where we don't really consider equilibrium. For strong acids and strong bases, we just assume that they split up completely. We don't care about their equilibrium constants because they're going to be huge. And the larger the Ka or the Kb is for the weak ones, the stronger that acid or base is considered. So the bigger the K value, the more product favorite it's going to be, and the more hydrogen ions or hydroxide ions are being produced in those equilibria. So some of the common strong acids are hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, so the three halogen acids. HF is a weak acid, but we'll talk about that later. And then nitric acid, sulfuric acid, and perchloric acid. There's sort of two types of strong acids. The HCl, HBr, and HI we call binary acids because they involve two elements. And then HNO3, H2SO4, and HClO4. These are called oxo acids. And we'll talk about the differences between those later. And then strong bases, you'll notice here lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. They're all group 1 or 2 metal hydroxides. So I would like you to familiarize yourself with these or memorize them if you can. It's good to know which ones are strong and which ones are weak. You don't need to memorize the weak ones. Anytime you're given like a Ka or a Kb for something, you can basically tell if it's going to be a weak acid or a weak base or not based off of the value of the K. But I'm also going to talk about what makes these particular things strong or weak a bit later in this lecture. All right, and you might know this, but the acidity or basicity of a solution is usually represented by its pH. And the pH is related to the amount of hydrogen ions or hydroxide ions present in the solution. And this is usually either measured with a pH meter, which measures the amount of ions directly, or with litmus paper, which is a type of paper that has like a certain chemical on it that changes colors depending on if there's hydrogen ions or hydroxide ions present in solution. And in general, if a pH is below 7, we consider that solution to be acidic. If it's above 7, the solution is basic or alkaline. And if the pH is equal to 7, we consider it to be neutral, which means it is neither an acid or a base, which doesn't mean that there aren't hydrogen ions or hydroxide ions present, but they're in equal concentration to each other to the point where they make water molecules and become neutral. So why is this, and why 7? Where did this value of 7 come from? Well, it's related to the dissociation of water molecules. So pure neutral water on its own does have a slight equilibrium where water molecules are splitting up into hydrogen ions and hydroxide ions. And this is called Kw, or the constant that we use for this is called Kw. And it's equal to 1 times 10 to the negative 14. So this K value is extremely small. So the water molecules are not splitting up to any real considerable extent. However, if we consider the equilibrium expression for this, we end up with Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And remember, the water does not appear in the equilibrium expression because it is a pure liquid that does not have a concentration. And we know since the H2O is splitting up to make one H plus and one OH minus, that the amount of hydrogen ions and the amount of hydroxide ions in solution are going to be equal to each other. So if we consider that H plus is equal to OH minus, we can solve for it. If this is equal to 1 times 10 to the negative 14, we can call this like x squared basically and solve for x, which is going to be 1 times 10 to the negative 7 molar for the hydrogen and hydroxide ion concentrations. So in neutral water, there is a very dilute but equal concentration of both hydrogen and hydroxide ions. Now pH is a logarithmic scale, meaning it is something that turns an exponential relationship into a linear relationship. And the way we calculate it is the pH is going to be equal to the negative log of the hydrogen ion concentration. So for neutral water, which has a hydrogen ion concentration of 1 times 10 to the negative 7 molar, if we plug that in and then do the negative log of it, we end up with 7. So that's where this value comes from. So if we apply the logic of the common ion effect, remember that the common ion effect says that if we have a solution at equilibrium that has multiple ions in it, and if we add a new solution that has one of those same ions in it, increasing the concentration of that ion, it's going to decrease the concentration of the other ion. So if we have water at equilibrium and we add either hydrogen or hydroxide ions to that neutral solution, the H plus is either going to increase or decrease depending on what's added, and that's going to change the pH. And since Kw is always going to be 1 times 10 to the negative 14 at 25 degrees Celsius, we can plug in our new concentrations and calculate what the concentration of the other ion is going to be. So for example, if the hydrogen ion is increased, the hydroxide ion is going to decrease. Since Kw is a constant, if this value goes up, this value is going to go down. And this explains why we have that whole below 7, above 7 situation. Because if the acid is in excess, here we have a hydrogen ion concentration that is more than the hydroxide ion concentration. If we plug in the hydrogen ion concentration, we get 6. And that tells us that this is below 7. And when acid is in excess, we're considered to have an acid solution or an acidic solution. For the base, if we switch these numbers and put the base in excess of the acid, and plug in the lower number for the hydrogen ion concentrations, we end up with 8, which is bigger than 7. So if the base is in excess, the pH is going to be above 7, and that's what's considered to be a basic solution. All right, so since this is a logarithmic scale, each number on the pH scale will be differing by a factor of 10. So like I said before, logarithms turn an exponential relationship into a linear one. And what that looks like in terms of pH is if you're comparing something with a pH of 6 to something with a pH of 7, the one with a pH of 6 is going to be 10 times more acidic. And a thing with a pH of 5 is going to be 10 times more acidic than something with a pH of 6, which means it's going to be 100 times more acidic than something with a pH of 7. And also, if the concentration is high enough, we can even end up with pHs that are negative. For example, if we have a 2 molar solution, negative log of 2 is going to be negative 0.30. So if you ever see a negative pH, that just means that it is extremely acidic, or basically most strong acid solutions in high enough concentrations are going to have negative pHs. Sometimes you're going to want to deal with a basic solution, and it'll be more relevant to the chemistry to consider hydroxide ions rather than hydrogen ions. So there's another similar value to pH called pOH that is calculated the exact same way. So the pOH is going to be equal to the negative log of the hydroxide ion concentration. And considering this is calculated the same way as pH, the scale is going to be really similar. So in this case, for pOH, if it is below 7, it's going to be considered basic. And if it's above 7, it's going to be considered acidic. It's going to be the opposite of the pH scale. So you can see here that low pH corresponds to high pOH, and low pOH corresponds to high pH. So there is a good math trick to know when you're doing the multiple choice section on the AP chemistry test, because you're generally not allowed the use of a calculator. So you're going to need to be able to calculate pH from the hydrogen ion concentration or the POH from the hydroxide ion concentration. But this is usually going to be when you're given simple concentrations. So for example, say your hydrogen ion concentration is 1 molar, aka 1 times 10 to the 0. Well, if we take the negative log of 1, we end up with a pH of 0. And if we have a hydrogen ion concentration of 0.1, aka 1 times 10 to the negative 1, we end up with a pH of 1. 1 times 10 to the negative 2 corresponds to 2. 1 times 10 to the negative 3 corresponds to 3. And I'm sure you could see the pattern here. Whatever the number that we're multiplying times 10 to the negative of is going to end up equaling our pH. And this usually only works when the integer for these values written in scientific notation is 1. So say we were given a pH, or say we wanted to know the pH of a sample with a concentration of 0.00000001. If we turn this into scientific notation and see what our times 10 to the negative value is, we can correlate that with its pH. So 1, 2, 3, 4, 5, 6, 7, 8. This is going to be 1 times 10 to the negative 8. So from that, we can assume, without a calculator, that the pH of this solution is going to be 8. So since the hydrogen and hydroxide ion concentrations are inversely related, we can also relate them through the following logarithmic property. You don't need to know where this comes from, but the log of x times y is equal to the log of x plus the log of y. And if we apply that to our equilibrium expression, and we do the negative log of kW, that's going to be equal to the negative log of H plus times OH minus, which is going to be equal to the negative log of H plus the negative log of OH minus. And if you look at these, this is just the expression for pH, and this is just the expression for POH. And the log of Kw, or the negative log of Kw, we can call pKw by the same logic. So that means that the pKw is equal to pH plus POH. And since Kw is equal to 1 times 10 to the negative 14, the negative log of that is going to be 14. So therefore, we have the expression pH plus POH is equal to 14. And this is helpful because if we know the pH and we don't know the POH, we can just subtract the pH from 14 to get the POH and vice versa. So if we want to calculate the pH for strong acids and bases, it's going to be pretty simple because we can assume that since they're strong, they're splitting up completely, and that tells us that the concentrations of the hydrogen or hydroxide ions are going to be equal to the concentrations of the original solution. For example, if I have hydrochloric acid and I make a 0.5 molar solution of it, I can assume that the hydrogen ion concentration is also going to be 0.5 molar since it's all splitting up, and H plus is going to be 1-to-1 with HCl. So then I can just do the negative log of the original concentration to get the pH. And if I wanted to do the reverse of it, if I knew a solution of a strong acid had a pH of 2, I can just do 10 to the negative pH, which would be the inverse log, to get the concentration. So 10 to the negative 2 is equal to 0.01 molar. Now, this logic is mainly applied to the first proton that comes off of something. If you have a multiprotic strong acid like H2SO4, both H's don't come off with the same amount of strength. The conjugate will be weak. HSO4 minus is going to be a weak acid. So we only really consider the first H plus coming off of a multiprotic acid when we apply this logic. If we want to look at HSO4 minus, we're going to have to look at the Ka for that. So let's try a practice problem. So say we want to calculate the pH of a 0.01 molar solution of sodium hydroxide, assuming that sodium hydroxide is a strong base. Well, with this assumption, we can infer that the concentration of the hydroxide ion is equal to the concentration of the original sodium hydroxide. So that means we're going to have 0.01 OH minus, but we want to know the pH, which is going to be related to the H plus. So we're going to have to use some of our equations to relate that. Now, based off of the equations that I've shown, there's two clear ways to do this. The first method would be to apply the Kw equilibrium expression. So since we know that Kw is equal to 1 times 10 to the negative 14, and we can plug in the hydroxide ion concentration to 0.01. We can solve for H+, which in this case is going to be 1 times 10 to the negative 12. And then if we do the negative log of that, we're going to get a pH of 12. The other way to do this would be to apply the pH plus pOH is equal to 14 expression. If we know the hydroxide ion concentration is 0.01, we can calculate the pOH, which will be 2. And we know that pH plus 2 is going to be equal to 14. So we can subtract 2 from 14, and we end up with a pH of 12. So you can see here we applied different methods and got to the same answer. All right, let's try another one. What is the concentration of a monoprotic strong acid, meaning it has one hydrogen attached to the anion, with a pH of 4.4? Well, I know that I can use the sort of inverse log version of the pH expression. So 10 to the negative pH is equal to the hydrogen ion concentration. So I can just do 10 to the negative 4.4, which will give me 3.98 times 10 to the negative 5 molar. And since we had two sig figs here, I'm just going to round that to 4.0 times 10 to the negative 5 molar H+. And since this is a strong acid and it's monoprotic, meaning there's a 1-to-1 ratio of the hydrogen ion to the original acid, we can assume that the concentration of the original acid was 4.0 times 10 to the negative 5 overall. All right, so I mentioned earlier that Kw is always 1 times 10 to the negative 14 at 25 degrees Celsius. Well, this is an equilibrium constant, and equilibrium constants are temperature dependent. So the dissociation of water is also going to be temperature dependent. If we look at this table here, we can see as we increase the temperature, the Kw starts to go up. And since the value is getting bigger, not by much, we could still imply that or infer that this is a endothermic equilibrium. Adding more heat to it is going to increase the amount of H plus and OH minus that is produced in the solution. And since they are always going to be equal to each other in a neutral water solution, even though the H pluses and OH minuses are increasing, they're still going to remain equal and they're still going to be neutral. This ends up having an odd impact because we usually calculate pH based off of the hydrogen ion concentration. And the hydrogen ion concentration is increasing with temperature. That means that the pH is going to go down. But since the hydrogen ion concentration and the hydroxide ion concentration are still equal based off of this equilibrium, the pH is going to go down while still remaining a neutral solution. So basically, if you increase the temperature, the number of the pH that's considered to be neutral is going to slowly drop. For example, say at 50 degrees Celsius, our Kw is 5.47 times 10 to the negative 14. If I use that in the equilibrium expression and solve for the hydrogen and hydroxide ion concentrations, I'm going to get 2.339 times 10 to the negative 7 molar. And if I plug that into my pH expression, I end up with 6.6. So in this case, 6.6 is still neutral, even though it's below 7, because we're at a higher temperature and our equilibrium constant has changed. All right, now it's time to talk about weak acids and weak bases. Since these are based off of equilibrium, the calculations for these are going to be a little bit more complicated because we need to consider the equilibrium constants and the extent by which the acid is dissociating or the extent by which the base is gaining protons. And this picture here just shows you kind of the difference between what a weak acid solution and a strong acid solution is going to look like. If we start with our, say our HA in a strong acid solution, all of it's going to split up. Though there's a tiny few here that aren't split up, but the equilibrium mostly favors the production of the dissociated ions. Whereas with the weak acid, only a small portion of the HAs are splitting up into their individual ions. And for our equilibrium expressions, for Ka, for the acid equilibrium constant, it's always going to be hydrogen ion times the conjugate base of the acid over the equilibrium concentration of the original acid. And for the base one, it's a little bit weirder. Here we have Hb plus. That means that we have a base that has gained a proton, and it becomes positively, or the charge goes up by 1 towards the positive when it gains that H plus ion. So it's going to be the Hb plus times the hydroxide ion concentration over the equilibrium concentration of the original base. So let's look at an example of how to calculate pH for a weak acid. So acetic acid, also known as vinegar, is a weak acid and it dissociates by way of this equation. We have our acetic acid. It's going to interact with water. Since it's an acid, it's going to give up its hydrogen ion to the water. And we end up with acetate, CH3COO minus, and our hydronium ion, which remember is functionally the same thing as hydrogen ions in solution. And this has a Ka of 1.8 times 10 to the negative 5, which confirms that this is a weak acid. So say we wanted to calculate the pH of a 0.5 molar solution of acetic acid. To do this, we're going to need an ice table. So I can write out my ice table. I don't include the water, obviously, because it's not involved in the equilibrium expression being a pure substance. We start with 0.5 molar acetic acid, and we start with nothing for the hydrogen ion and the acetate ion. And since this is all 1-to-1, we're going to lose minus x on the reactant side and then gain plus x on the product side. So our equilibrium concentration of acetic acid is going to be 0.5 minus x, and the concentrations of the hydrogen and acetate ions are going to be equal to x. So I can set up my equilibrium expression. Ka is going to be equal to x squared over 0.5 minus x. And since this is a weak acid with a small Ka, we can assume that the amount of hydrogen ions being produced is going to be negligible compared to the original concentration. So the minus x here is going to be negligible compared to the 0.5. So we can delete the minus x in the denominator and just have x squared over 0.5. And when we solve for x using 1.8 times 10 to the negative 5 as our Ka, we end up with 0.0030. So that means this is our hydrogen ion concentration. So then to get the pH, I can then plug in that hydrogen ion concentration that we calculated from the equilibrium expression into our pH expression, and we end up with 2.5. And you can see this is drastically different than what we would have got if we just put in 0.5 as our hydrogen ion concentration, which would be incorrect because this isn't a strong acid. But it shows you the difference between the pH of a strong acid and a weak acid. All right, another way that the strength of weak acids and sometimes weak bases can be represented is by the percent of ionization. So this is when you take the hydrogen ion concentration, this should be a superscript, at equilibrium and divide it by the initial amount of acid, not the equilibrium amount of acid, like what you started with, and then multiply it by 100, you can get the percent by which it ionized or the percent by which it dissociated. For example, in that previous problem, we had 0.5 molar acetic acid to start with, and we calculated that the amount of hydrogen ion concentration that we produced was 0.003. So to calculate the percent ionization, we do 0.003 divided by 0.5 times 100, and we get 0.6%. So things like weak acids sometimes only dissociate by less than 1%, and that's just what the equilibrium is. So let's do another example for a weak base. So what is the POH and pH of a 0.1 molar ammonia solution? Ammonia, we discussed earlier, is a weak base. So it's going to behave in the Bronsted-Lowry weak base fashion, where it's going to accept a hydrogen from water or another chemical species. And in this case, we have water. The hydrogen ion is going to be pulled off of it. So we end up with NH4 plus and our hydroxide ion. And our Kb in this case is 1.77 times 10 to the negative 5. So I can do a similar thing. I can apply an ice table. We start with 0.1 here. We start with nothing here. This one is all 1-to-1 as well. So minus x plus x plus x. We end up with 0.1 minus x as our equilibrium concentration for the ammonia, and then x for hydroxide and ammonium. We can apply the same logic that we applied to the acetic acid example earlier. We can omit the minus x from the denominator and have x squared over 0.1. We can plug in our Kb and then solve for x, which in this case is 0.00133. And then I can plug that in from a hydroxide ion concentration into the POH expression. And I end up with a POH of 2.9. And since the problem also asked me to calculate pH, I can just do the pH plus POH is equal to 14 expression. and subtract the POH from 14 to get the pH, which in this case with 2 sig figs is going to be 11. Now, if you know the Ka, you can also determine the Kb for the conjugate base of the weak acid, and vice versa. If you know the Kb, you can also determine Ka for the conjugate acid of the weak base. So what I mean by that, so consider this equation here. This is a generic acid equation where I have HA interacting with water. It's going to donate its hydrogen. We end up with A minus, which is our conjugate base of our original acid, and then hydronium. And my equilibrium expression for that is going to be Ka is equal to the conjugate base times hydronium, aka H plus, over the original HA. And then for a conjugate base equilibrium, the A minus is our conjugate base. That's going to interact with water and take a hydrogen from it. And we end up with HA again and hydroxide in the solution. And our equilibrium expression here is going to be Kb is equal to HA times OH minus over the original conjugate base. Now, there's a cool math trick that we can do here. If I take Ka and Kb, both of these equilibrium expressions, and I multiply them by each other, so Ka times Kb, I end up with this, where I have A minus times H3O plus times HA times OH minus over HA times A minus. The HA here and the HA here are going to cancel, and the A minus here and the A minus here are going to cancel. And what I'm left with is just H3O plus and OH minus, aka H plus times OH minus, which we know equals Kw. So that tells us that Ka times Kb is going to be equal to Kw for a conjugate pair. So let's look at our acetic acid example again. We know that the Ka for acetic acid is 1.8 times 10 to the negative 5. And say we wanted to calculate Kb for acetate, the conjugate base of acetic acid. Well, I can apply this expression. So since Ka times Kb is going to be equal to Kw for the conjugate pair, I can plug in Ka and then solve for Kb, which in this case is going to be 5.6 times 10 to the negative 10. So this would be the equilibrium constant if we were describing this process here, where the conjugate base is interacting with water, stealing a hydrogen from it, and becoming acetic acid again, and producing hydroxide. And sometimes the strength of weak acids and bases can also be represented by an alternative value called pKa or pKb. And like we saw with pKw earlier, this is calculated the same way as pH or POH. Basically, anything that has the little p in front of it means you negative logged something. So pKa is equal to the negative log of Ka, and pKb is equal to the negative log of Kb. And these values, the way they're used, the smaller the pK or the smaller the pKb, the stronger the acid or base, much like we know the bigger the Ka or the bigger the Kb, the stronger that acid or base. And we can apply some familiar logarithmic logic that we did earlier. We know that Kw is equal to Ka times Kb, and if I negative log both sides of this equation, so negative log of Kw, which we know is equal to pKw, aka 14, is going to be equal to the negative log of Ka times Kb, which is the same thing as negative log of Ka plus negative log of Kb, which are just our pKa and pKb expressions. That tells us that 14 is equal to pKa plus pKb, much like 14 is also equal to pH plus POH. And a way we can apply this is, so we did that problem earlier where we calculated what the Kb of the acetate would be. Well, we could solve that in another way. So we know that the Ka for acetic acid was 1.8 times 10 to the negative 5. And if I calculate the pKa of that, I can negative log that. I end up with 4.74. And I know that 14 is equal to the pKa plus the pKb. So I can subtract 4.74 from 14, and I end up with a pKb of 9.25. And then I can calculate what the Kb would be by doing the inverse log of the pKb expression. So 10 to the negative 9.25 is going to be equal to 5.6 times 10 to the negative 10, which is the same answer that we got earlier. I do think this is a little bit more cumbersome of a way to calculate Kb of the conjugate base from Ka, but it's just another tool that we have. And speaking of that, Due to all these various relationships, they're all like interrelated. We have multiple tools to solve for unknown quantities, depending on which things we know. I believe all of these are on your equation sheet. So just remember that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, and then the pH plus the pOH is equal to 14. And then we have a similar relationship with our equilibrium constants. Ka times Kb is also equal to Kw, and 14 is equal to the pKa plus the pKb. All right, now let's take a little break from math for just a moment and talk about chemical equations. So when an acid and a base are mixed, the acid donates its protons to the base usually, and this is called a neutralization reaction. We already talked a bit about this in Unit 4, but we didn't really talk much about the strengths of acids and bases and how that affects the equations. So let's look at some examples of all of the different combinations of neutralization reactions that we can have. So obviously we can have strong acids and strong bases interacting, but we can also have a strong acid interacting with a weak base, a weak acid interacting with a strong base, and then a weak acid interacting with a weak base. So let's go over an example of each of these. So the strong acid and strong base combination is the most simple. So if we have hydrochloric acid, which is a strong acid, interacting with sodium hydroxide, which is a strong base, we're usually just going to end up with water and a ionic salt, because the hydrogen ions from the HCl are going to combine with the OH minus from the strong base, and they're going to form a water molecule. And if we look at the complete dissociation and then come up with our net ionic equation, for a strong acid, strong base combination, we're basically always going to have the net ionic equation of hydrogen ions plus hydroxide ions making water. The only exception of this, which I can't even think of one off the top of my head, is if a precipitate is formed, because then we can't cancel that out of the net ionic. But the basic thing that's happening with strong acids and strong bases is hydrogen and hydroxide combining to make water. And if you do a strong acid, strong base reaction, the pH of the resulting solution is always going to be dependent on the final concentration of the excess reactant. Say if we have like a 1-to-1 ratio here, if they're in equal proportions, the pH is going to be 7 because there isn't going to be an excess reactant. But if one of these is in excess, either the acid or base, we're going to use how much is left over to calculate the pH of the final solution. We'll talk a bit about that in a moment. So if I have a strong acid and a weak base, the strong acid is going to donate its proton to the weak base. So we're going to end up with something like this, where the hydrogen is giving, or sorry, the HCl is going to give its hydrogen to the NH3 to form ammonium chloride. And if we do the net ionic equation, it's basically just H plus ammonia making ammonium. So the product in this case is just the conjugate acid of the weak base. Now, if we want to know what the pH of the solution is going to be after this happens, we're going to need to know what's in excess. If the strong acid is in excess, the pH will be based on the concentration of leftover hydrogen ions, because the ammonia is going to be completely converted into ammonium, and we're going to have some H plus left over. However, if the weak base is in excess, the pH is going to be based on the equilibrium and the ratio of the weak base to its conjugate acid, and it's going to get a lot more complicated. And we're not going to talk about that one today. So for a weak acid and a strong base, sort of the opposite here. Here we have a weak acid of acetic acid interacting with NaOH, which is a strong base. And we're going to end up with the conjugate base of the weak acid, and then some sodium ions and a water molecule. And our net ionic equation is basically just going to be the hydroxide stealing the hydrogen from the weak acid to make water. And then we end up with our conjugate base of the weak acid. And if we want to know what the pH is after the mixing here, if the strong base is in excess, we're going to base the pH off of the leftover hydroxide ions. But if the weak acid is in excess, much like the last example, it's going to be based on equilibrium and the ratio between the weak acid and its conjugate base, and it's going to be a lot more complicated. Lastly, if we're looking at a weak acid, weak base reaction, basically the equation is going to be simple. The hydrogen ion is just going to go from the acid to the base, and we're going to end up with a conjugate base for the weak acid and a conjugate acid for the weak base. But if we want to do any calculations with this, it's going to be complicated, like I mentioned earlier. It doesn't matter which one is in excess. We're going to have a complicated equilibrium thing going on, and I'm going to talk about that in part 2. So let's look at the math for a neutralization reaction. Since I mentioned before that the resulting pH of a neutralization reaction is going to be dependent on what's in excess, this is pretty simple when the strong thing is in excess, and it's going to be really complicated when the weak thing is in excess. And we're going to mainly focus on the strong thing being in excess today. So, for example, say I have 15 milliliters of a 2 molar sodium hydroxide solution, and we mix that with 20 milliliters of a 1 molar hydrochloric acid solution. And say we want to calculate what the resulting pH of this mixed solution is. We can already see that we probably don't have equal proportions, so we're going to have to do the math to figure out what's left at the end. So for our sodium hydroxide, we have 2 moles per liter times 0.015 liters. That gives us 0.030 moles of sodium hydroxide overall. Do the same calculation for the hydrochloric acid. 1 mole per liter times 0.02 liters, we end up with 0.02 moles of hydrochloric acid. Based off of the chemistry here, this is going to be 1-to-1 since the hydrogen is going to combine with the hydroxide to make a water molecule. And we can see that the amount of moles are not 1-to-1. We have an excess of sodium hydroxide in this case. So since our HCl is going to be our limiting reactant and it's 1-to-1, 0.2 moles of the HCl will neutralize 0.2 moles of the sodium hydroxide, and we're going to have a leftover of 0.01 moles of sodium hydroxide at the end. And since we mixed two solutions together, we need to consider the final volume, which in this case is going to be 35 milliliters, because we combined 15 milliliters plus 20 milliliters. So then I can calculate the concentration by dividing 0.01 by 0.035 liters, and I end up with a final concentration of hydroxide of 0.286 molar. Now, I know since this is a strong base that the amount of hydroxide is going to be equal to the amount of sodium hydroxide. So then I can plug that into my pOH expression. That gives me a pOH of 0.540. And then I can calculate the pH by utilizing the pH plus pOH equals 14 expression. And I end up with a pH of 13.5. I end up with a basic solution. And this makes a lot of sense because the base canceled out all of the acid, but we still had a bunch of base left over in solution. So we ended up with an overall basic solution. Let's try another one. What is the pH of a solution resulting from mixing 150 milliliters of 0.015 molar hydrobromic acid and 200 milliliters of 0.01 molar potassium hydroxide? So this is another strong acid, and this is another strong base. So we can apply similar logic as the last one. We can calculate the moles of each. So we end up with 0.00225 moles of HBr and 0.00200 moles of KOH. We can see here this time that the base is our limiting reactant and the acid is our excess reactant. This is also going to be 1-to-1 since the hydrogen ion is going to combine with the hydroxide ion to make water. So I can subtract 0.002 from 0.00225 to figure out how much of the hydrobromic acid is going to be left over at the end, which is going to be 0.00025 moles of HBr. And I know that the final volume of the solution is going to be 0.15 liters plus 0.2 liters, which is going to be 0.35 liters. I can get the leftover hydrogen ion concentration, which I can then put into my pH expression, and I end up with a overall pH of 3.2. So that makes sense that our final pH is below 7 because it's an acidic solution because the acid was in excess. So now let's try another one. What is the pH of 100 milliliters of 2 molar sodium hydroxide if it's added to 25 milliliters of 4 molar acetic acid? So this time we have a strong base interacting with a weak acid, and we have the Ka value for that weak acid. Well, let's think about it. So if we take our sodium hydroxide values, we end up with 0.2 moles of sodium hydroxide. And for the acetic acid, we end up with 0.1 moles of acetic acid. And you can see here that the strong base is in excess of the weak acid. And there's going to be 0.1 moles of the sodium hydroxide left over because the 0.1 moles of the acetic acid are going to react with 0.1 moles of the sodium hydroxide, and I'm going to have 0.1 moles of the sodium hydroxide left over. And our final volume is going to be 125 milliliters because we had 100 milliliters interacting with 25 milliliters or being mixed with 25 milliliters. So then I can take my 0.1 moles of sodium hydroxide left over, divide that by the total volume, gives me 0.8 molar sodium hydroxide, and then I can do my pOH expression. I get a pOH of 0.097. So this is an extremely low pOH, which is going to tell us our final solution is super basic. And with sig figs considered, my pH is still 14 because subtracting minus 0.097 is not going to drop it down to the next value. Now, you might notice here that the Ka of the weak acid didn't come into play at all. I didn't care that this was a weak acid. I didn't care about that equilibrium because it was interacting with a strong base. Every bit of strong base that I added to that weak acid ended up neutralizing it, and it didn't really matter what the equilibrium was. Because every time an H plus ion was neutralized, the acid released more to maintain the equilibrium until it ran out. And the reasoning for this is based off of Le Chatelier's principle. Because if we consider a dissociation equilibrium, HA is going to split up into hydrogen ions plus hydroxide ions. And there's always going to be a certain amount of H plus present in the solution based off of this Ka. And if I add base to it, the hydrogen ion is going to become neutralized because the hydrogen ion is going to interact with a hydroxide ion to make a water molecule. And if we remember back to Le Chatelier's principle, if I remove something from one side of an equilibrium, say the H plus in this example, the equilibrium is going to shift to make more of that thing in order to try to maintain the equilibrium constant. So every time I add hydroxide to the solution, I'm removing H plus to the solution, and the equilibrium is going to continue to shift right to make more H plus. And if the hydroxide is in excess, this is basically going to keep happening until all of the HA ends up getting dissociated and all of the hydrogen ions end up getting neutralized. All right, and I kind of mentioned this earlier, but calculating the pH when a weak acid or base is in excess is a lot more complicated. So that's going to be sort of the focus of Unit 8, Part 2. So we'll get to that in the next video. All right, so finally, I want to talk about what the deal with strong and weak acids and bases is anyways, and why the extent of dissociation can vary. So let's look back at our list of common strong acids. We have hydrochloric acid, hydrobromic acid, hydroiodic acid, and then nitric, sulfuric, and perchloric acid. And we have sort of two categories of acid here. We have the oxo acids, which are HNO3, H2SO4, and HClO4. They all end up with a name like nitric, sulfuric, perchloric. Sometimes you have nitrous, sulfurous, or chloric or chlorous. They usually have the same sort of naming convention. And these are all hydrogen bound to an oxygen containing a polyatomic anion. And these differ from the binary acids, which are HCl, HBr, HI, which are all hydrogen bound to a single element anion. And those always have a similar name, hydrochloric, hydrobromic, hydroiodic. And let's look at the trends for these and why these are considered to be strong. So let's focus on nitric acid first. So we can tell if a hydrogen is going to dissociate from an acid molecule dependent on how strong that bond is of the hydrogen atom to the rest of the molecule. And it's going to be more likely to split from the molecule in the case of a strong acid if the bond between the hydrogen and the rest of the molecule is weak. So, for example, nitric acid, HNO3, is a strong acid, but nitrous acid, HNO2, is weak. And let's look at their structures. So even though the H is written on this side, the H is actually connected to the O in all of these cases, and you'll see that if you go through the work to draw the Lewis structure and figure out what the optimal arrangement of the atoms is. In this case, we have hydrogen bound to oxygen, and then the oxygen is bound to nitrogen and two other oxygens. Whereas with nitrous acid, we have hydrogen bound to an oxygen, and that's bound to one nitrogen and one other oxygen. Like I said, in both cases, the hydrogen is attached to the oxygen, which is then bound to the rest of the molecule. And the hydrogen ions, aka the protons, they have no electrons themselves, so they're going to want to share a pair of electrons from something else in the rest of the molecule. In this case, the oxygen is going to donate a pair of its electrons to make a bond with the hydrogen. And the strength of this bond is going to be based off of the electronegativity of the rest of the molecule. And in both of these cases, we have nitrogen bound to a bunch of oxygens. And these oxygens themselves are pretty electronegative. And that's going to affect this bond here because electrons are going to be pulled away from this bond towards the rest of the molecule. And the less that the proton sees of the electrons in the acid, the more likely the proton is going to be to dissociate because the H plus is chilling here on the molecule and it has a choice to either stay here on the molecule or try to jump off the molecule and jump onto a water molecule to make hydronium. And it's going to depend on what is a stronger pull for that hydrogen ion. And if in this case, the electrons are being pulled towards the rest of the molecule, and the more electronegative the rest of the molecule is, the less that hydrogen ion is going to see those electrons, and therefore the weaker the bond is going to be. And since oxygens are particularly electronegative and greedy for electrons, the more oxygens we have bound to this anion, the more electrons are going to be pulled towards this side of the molecule and away from the hydrogen, and therefore the weaker that connection between the hydrogen and the rest of the molecule is going to be. So that explains why HNO3 is more likely to lose its hydrogen than HNO2 is, because there's more oxygens here, there's more greedy electronegative elements, electrons are going to be pulled away from this HO bond, and this H is going to want to go somewhere else to get electrons because it's not getting electrons shared with it. Whereas here, it's also going to be an acid, it's also going to split up, but it's not going to split up to the same extent because in this case, since there's one less oxygen, there's a little bit more even sharing, and the hydrogen will be able to see those electrons a little bit more. This also explains why perchloric acid, HClO4, is a strong acid, whereas HClO3, which I think is chloric acid, HClO2, which is chlorous acid, I think, and then HClO, which is hypochloric acid. Why the three of these are weak and this one is strong? Same explanation. This one has the most oxygens on it, which is going to make this anion super electronegative and hog the electrons, and the hydrogen is barely going to be able to see them, so it's just going to dip. It's just going to leave. Whereas here, the hydrogen is going to see those electrons a little bit more because the rest of the molecule is slightly less electronegative than the HClO4 is. And by a similar logic, we can compare HClO, HBRO, and HIO in terms of acid strength. And the chloric is going to be, or the HClO is going to be a stronger acid than the bromine or iodine versions of it because the chlorine is going to be more electronegative than bromine, which is going to be more electronegative than iodine. So in this case, even though this is way weaker than these other ones, it's still going to be stronger than similar molecules that have weaker or less electronegative halogens. So the electrons are going to be shared a little bit more in the molecule. So therefore, we can kind of say that the more electronegative the halogen in the oxo acid is, the stronger the acid is going to be overall. All right, and the binary acids have a bit of a different trend. So if we look at acid strengths, it's observed that HI is stronger than HBr, is stronger than HCl, is stronger than HF in terms of acid strength. And this seems kind of like the opposite trend of the oxo acids, because in the oxo acids, the stronger the electronegativity of the halogen was, the stronger the acid was overall. Whereas here, the one with the least electronegative ends up making, the one that is the least electronegative ends up making the strongest acid. And this does have to do with electronegativity. You can see that there is a trend, like the least electronegative one is going to make the hydrogen less strongly attached to it, which means that the hydrogen is going to leave, whereas hydrofluoric acid is a weak acid compared to these three, which are all strong acids, because the F is super electronegative and it's going to attract that hydrogen more strongly. But the reasoning here is actually more to do with the size and Coulomb's law, because the bigger the anion is in this binary acid, the weaker the Coulombic force is going to be, because the bigger the distance between those two atoms, and therefore the weaker the force. So if this is HF, this is HCl, this is HBr, and this is HI, you can see there's a much bigger distance between the hydrogen and the iodine as there is between the hydrogen and the fluorine, which means that the overall attraction between those two atoms is going to be much weaker. And the weaker the attraction of the hydrogen to the rest of the molecule, the stronger the acid, because it's not going to be held onto it very tightly. So let's talk about bases now. So all of the strong bases contain hydroxide ions, and basically as long as they're able to dissolve, they're directly going to make the solution more basic by dissociating. And like I mentioned before, these all involve metals from group 1 and 2. So all of our strong bases are going to be lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So you just need to know this, that all of the strong acids are hydroxide plus a metal from group 1 or 2. Now for the weak bases, it's a little bit more complicated. They all produce hydroxide indirectly by interacting with water or another molecule. So for these, we need to consider the same logic for the acid strength, but backwards. Because the weaker the conjugate acid of the base, the stronger the base is going to be. Because if the base here is going to take hydrogen from H2O to make this BH+, the weaker this is, the more the hydrogen is going to be held onto it, and the more likely it is for this to be formed and stabilized. And it's not going to want to go in the other direction, making this base much stronger. So let's look at an example here. Consider these weak bases. So we have CH3, NH2, 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 and then HO, NH2, and then Cl, NH2. Here we have the bases. These are what their conjugate acids are going to look like. Here they've all gained a hydrogen. And based off of their conjugate acids, let's figure out which one of these weak bases will be the strongest and have the largest Kb. And this is going to be based off of the stability of the conjugate acid. Like I said, the weaker the conjugate acid is going to be, the stronger the original base is going to be. So let's look at these molecules. Here we have let's call this our hydrogen that was gained. The rest of this molecule is not electronegative at all. We have carbon. Here we have nitrogen, which is somewhat electronegative, oxygen, which is even more electronegative, chlorine, which is pretty electronegative. So in all of these cases, the rest of the molecule is kind of electronegative, which means that the electrons are going to be pulled away from the hydrogen, which is actually going to make all of these conjugate acids stronger than this one, which has carbon, which isn't very electronegative at all. So what that tells us is that the CH3NH2 is going to be the strongest of these bases because it has the weakest conjugate acid of the bunch, due to the fact that the rest of the molecule is not very electronegative, and the electrons are going to be shared more evenly, which is going to strengthen this NH bond, which will make it hold on to the hydrogen a little bit more and stabilize it in solution. Whereas in all of these ones, we have the nitrogen bound to something kind of electronegative, which is going to pull electrons towards that side of the molecule and weaken the bond with the H. All right, I know this was a long video, but that is all I have to say for part 1, and I'll see you in part 2.